All right, we have done one sample t-test. We've done independent sample t-tests. The question is, are you ready for a repeated measures t-test, which is also known as dependent samples, paired samples, and other names? Now, you might be wondering, hey, what's so special about this t-test? When am I supposed to use it? And I always tell my stats students it is a very good idea to not just know the steps of any given test, but also to be very familiar with when you're supposed to use a particular test, because you don't want to use the wrong test for the wrong set of data. Then you're going to get a garbage result, and nobody wants to spend time with that. So when would you use, I'm going to call it a repeated measures t-test. You're going to use this when you have two sets of scores, and with the t-test it can only be two because you can only compare two means, two values with a t-test. There is a test if you have more, but we'll get to that later. So you have two sets of scores. Well, hey, we had two sets of scores with an independent measures t-test. How is this one different? Well, with the independent measures t-test, you had two sets of scores from two completely separate groups of participants or subjects. In this case, your two sets of scores are from the exact same group or sample of participants or subjects. So they have been tested twice. They have been measured, assessed, scored, rated. They've been tested twice. So we have two sets of scores from the same source, the same people or animals, or if you're in any other field, some other source. All right, let's look at an example. Now, in the previous videos, I've been using the example of ACT scores. And so in this case, if we were going to be able to use a repeated measures t-test, remember they have to be from the same source. So I have additional information over here where I have a column where I have them labeled as client 1, client 2, client 3, and client 4. Now 4 is way too small a sample size in most research situations, but to keep things simple and to keep our computations short and simple, we're just going to have 4 scores. But in real research, you'd want to have more than that. I always like to remind people of that, especially if they do go into real research. They're like, whoa, I have so many scores in front of me. All right, so you've got these clients. What are they clients for? Well, they're going to an ACT prep program. And so in this case, they all went into the ACT prep program, paid their money, took some classes, and we have a pre and a post score. So before going into the program, they have a pre-existing ACT score. And so they're listed here, 19, 18, 20, and 18. And then we have post score. So this is after going through the program. They take the ACT again, and here are their scores, 21, 23, 25, and 22. So very importantly, these are paired. All right, so like client 4, this score goes with this score. They are matched, they are paired. You can also use this with a match design, which that's more of a research design class sort of topic, but there's this other design called match design. You could use this statistic for that. But since this is from the same person, the same source, these are not independent, so we wouldn't use an independent samples t-test. These are dependent scores because they come from the same person. Now, in looking at it, if I were to say, hey, does this program, this ACT prep program, basically is it worth the money? Does it actually raise ACT scores? Now, you might look at it and say, well, they're higher. They're all higher. So yes, it raises ACT scores. But when we're using our psychological statistics, we often want to know more than, hey, do they look higher? We want to know, are they statistically significantly higher? All right, so let's go ahead and figure that out. We're going to use our t-test to figure that out. We have to do a little prep work first. Previously, we used the actual individual scores for our computations. With a repeated measures t-test, we are going to compute a new set of scores that we're going to perform our computations on. We have to perform something called difference, not perform, we have to compute. We have to compute difference scores. Now, difference, you can probably guess, it involves a difference. What kind of difference? You take the second score minus the first score. Now, one of the most common mistakes that students will make that'll throw their answers off a little bit is they want to do first score minus second score. And every once in a while I'll mess up and do this because it happens. All right. Second score. All right. So score 2 minus score 1, or if you wanted to label these as x's, x2 minus x1. All right. So we need to compute some difference scores here. Be right back. All right. So I have computed a new column with capital D as the label. Capital D is a pretty common abbreviation for a difference score. And so this is just like 21 minus 19 equals 2. That's how we got this score of 2. Now, just if you can get positive or negative difference scores. If you get a positive score, that indicates that there was an increase in the score from time 1 to time 2, condition 1 to condition 2. And then if you get a negative score, that means the scores went down. So these are all positive. Our scores went up, which is what you would hope from an ACT prep type program. But we need to do our t-test. So what do we need to be able to do our t-test? Well, let's go ahead and write down the t-test formula. Oh, it started early. All right. So this is our formula for a repeated measures t-test. So we have our mean difference, and this capital M means sample mean. This is our sample. The sample is drawn from the population, but we're doing this type of test when we don't know the parameters of our population. If you don't know these terms, I've covered them in previous videos. They're usually covered in the beginning of a statistics course. So here we have this mu symbol, which is the population mean difference. Well, we don't know the population parameters. How do we know what to put here? Well, our null hypothesis, if you don't know, the null hypothesis is expresses the idea that basically there is no difference, no effect. So our null hypothesis is that this mu, this population mean difference, would be 0. So that actually makes our lives a little bit easier. Oh, it's in my hand. I was looking for my marker. That's in my hand. Since this is 0, I mean, it's in the formula, but you don't really have to do anything with it. It's just 0. All right, we do have to compute our sample mean difference. We know how to compute a mean, right? You remember how to compute a mean? You're going to add these different scores up and divide by n. What does n equal? It's the number of scores. N equals 4. By the way, we have this thing called the degrees of freedom, or I guess that's plural, degrees of freedom for any particular test that we're doing. For a repeated measures t-test, degrees of freedom, like it often is, would be n minus 1. So our degrees of freedom, or df, degrees of freedom, n minus 1, 4 minus 1 is 3. That's not a whole lot of degrees of freedom, but remember, we're using a teeny tiny sample size here. All right, so we know how to compute our numerator. We need our denominator. This is the estimated standard error of the mean difference. How do we get that? That's going to be a bit more of a lengthy formula. All right, but first, let's go ahead and compute our mean, because we know how to do that. It makes us feel good to do the stuff that we definitely know how to do, usually. All right. Our mean difference is 4. If you don't know how I got that, 2 plus 5 plus 5 plus 4 equals 16 divided by n, which is 4. So that's how we got that mean difference. So that's what's going to go up here. We need to talk about how to get this number, and that's the longer part of the computations. Right, so I've drawn little pathways here so we can see what numbers we need to get. So we need to know the standard error of the mean difference. The formula for the standard error of the mean difference is the square root of variance over n. S squared, if you don't know that abbreviation, that stands for variance. Specifically in this case, we're talking about the variance of the difference scores, not the individual scores. Once you have computed different scores, we are going to ignore these original scores over here. Our interest is now in the difference scores. So we need to compute variance over n, which we already know that n is 4. So how do we compute variance? If you need a refresher, variance is sum of squared deviations over degrees of freedom. Now we know our degrees of freedom is 3. We need to compute this SS, this sum of squared deviation scores. We need to compute deviation scores, we need to square them, and then we need to sum them. So I'm going to do that, and I will be back. All right, I'm sitting on a different chair over here, and I'm aware of the glare. I'm avoiding the glare here. All right, so our different scores. We have our different, I'll move some things over here. We've got our different scores, 2, 5, 5, and 4. We need to compute something called a deviation score. If you don't know, a deviation score is just the score minus the mean. In this case, it's going to be the difference score minus the mean difference. Remember, mean difference equals 4. So we have 2 minus 4, 5 minus 4. That's how we get these numbers, -2, 1, 1, and 0. All right. I always have that moment where I'm like, I did that right. This is simple math. I can do that. All right, now what do we do next? We have to square each one of these deviation scores. So this column is for the squared deviation scores. So -2 squared is 4. 1 squared is 1. 0 squared is 0. So these are our squared deviation scores. Now this number that we need for our variance, this SS stands for sum of squared deviations. So we sum this. Sum just means add it up. So we add up 4 plus 1 plus 1. That's how we get SS equals 6. SS equals 6. Good. Now we can compute our variance. I know you're excited. I'm excited. Let's compute a variance. We now have a variance. So remember, variance is sum of squares over degrees of freedom. So that would be 6 over 3 because degrees of freedom is n minus 1, n equals 4. 4 minus 1 is 3. Every once in a while, somebody will say, hey, why are you talking to us like we don't know anything? I would rather take that approach than go too fast for someone who needs me to slow down. If you already know this stuff, good. It should make you feel good. You already know some stuff. So 6 divided by 3, 2. So our variance is 2. Variance is 2. We're not done yet because variance is just part of the equation for the estimated standard error, which is the denominator of our t statistic. So we now have to compute that part. Now we know our denominator. So the estimated standard error is the square root of the variance over n. Our variance was 2. Our n is 4. So 2 divided by 4 is 1/2 or 0.5. The square root of 0.5 is 0.71. So now we can plug in 0.71 into our formula here. So now we have a t statistic. T equals 5.63. How do we know that? Because it's the mean difference minus the population mean difference, which is 0, so we don't have to really worry about it. So we have our mean difference, which was 4, divided by our standard error, estimated standard error of the mean difference, which is 0.71. So 4 divided by 0.71 is 5.63. By the way, I am rounding to 2 decimal places consistently because that's how I do it in my class. If you were viewing from another class, you're going to go with whatever standard your instructor calls for. For example, I know a lot of chemistry classes, you're not supposed to be doing all that rounding. You're supposed to use all the decimal places, but in my class, we round to 2 decimal places. That's just, my class. So what do we do with this number? Is it a good number? We need to figure out if it's statistically significant. We got to look at a t distribution table to see if this is high enough to be considered statistically significant. All right, I've got the t distribution table in front of me. I am going to put it up in editing as a sticker. Hopefully I remember how to do that. It's probably going to cover up the board here. All right, so we've got t equals 5.63. We need to look up something called the critical value. What's the minimum number that we need to get that we consider it a statistically significant t statistic, which means the difference that we analyzed is a statistically significant difference, statistically significant change or improvement from time 1 to time 2. All right, so first of all, The things we need to do when we're looking up our critical value, first of all, we need to know our degrees of freedom. We know that. We've got that. Degrees of freedom equals 3. The other important things we need to know is we need to know if we are performing a one-tailed test or a two-tailed test. And actually, this is the sort of thing you figure out before you begin. So let's just pretend we did all this before we began with our computations here. All right, so a two-tailed test is where you just expect difference. A one-tailed test is appropriate when you expect difference in a particular direction, like you expect decrease, but increase wouldn't make sense, or you expect increase and decrease wouldn't make sense. In this case, it really doesn't, if you're testing a program that's supposed to raise ACT scores, it really doesn't make sense that you would see a decrease in ACT scores. You certainly hope not. So you're really hoping to see that you have an increase in one direction of ACT scores. So it would make sense to do a one-tailed test in this case. If we were just like, hey, we don't know what direction, we just think it might change from time 1 to time 2, then you can do a two-tailed test. But this would make sense as a one-tailed test. Now, the other important thing is we need to know something called the alpha level. The alpha has to do with our risk of making what we call a type 1 error, which is like a false positive when we say there's an effect when there really is an effect. We want a tiny risk of a type 1 error, and it's pretty standard to say we don't want to go any higher than a 5% risk of that. And so alpha set to 0.05, alpha equals 0.05 means that you want a number that doesn't go above that risk. Sometimes this confuses students, and that's okay. We're basically hoping that this is an unusual number. We're hoping that this is a low probability number that is far enough away from 0 that we can say this isn't just sampling error we're detecting. This is an actual effect that we're detecting. So we do that if we have a nice low probability t-statistic. All right, the low probability we're going to go for is 0.05 or less than 5%. You can use other percentages, like you can be really stringent and say alpha equals 0.01. I only want a 1%, or I want less than a 1% risk of making a type 1 error. We're going to go with 5%. It's pretty standard. So we're going to have our alpha set to 0.05. If you are taking statistics, your instructor should be talking about significance testing and alpha levels, all right? But I'm thinking of making separate videos about things like the null hypothesis, what does that mean, and significance testing. All right, right now we're just focusing on the steps. We're focusing on how do you get from start to finish, how do you do a t-test and know if your results are significant or not. So we look in our table, we look for a one-tailed test. So we make sure that we're looking at the table or the part of the table for a one-tailed test. We make sure we're looking under alpha equals 0.05. And we look under degrees of freedom of 3 to see that we need to get a t-statistic of at least 2.353. Did we do it? Is 5.63 higher than 2.353? Yes, it is. Yay! We have a statistically significant improvement. By the way, these are made up data. This ACT prep program does not exist. I just made it up. All right. But if it were real, we could be like, hey, look at that. They could get excited and say, we have evidence for a statistically significant increase in ACT scores with this teeny tiny sample here. All right. So that's how you do a repeated measures t-test. Now, what if you wanted to know about effect size? I'm going to do that in a separate video. All right, but you could also figure out the size of the effect in addition to whether or not it's statistically significant. All right, folks, I hope you had fun doing stats with me. Stats is always fun, which for some students, that's a joke. For some students, they're like, yeah, it can be fun. But I know most of my students don't particularly find stats enjoyable, but it is important for the field because if you are to do something like, say, maybe you're testing a therapy of some sort. Maybe you're testing a school intervention. Maybe you're an industrial organizational psychologist and you consult with a company to try to improve something about the company. You may be looking at before and after. You want to show that the before and after are significantly different. So knowing how to do statistics, how to interpret statistics is relevant and important for psychology, even though a lot of people don't know that or have awareness of that when they start in psychology. But we don't just do it to make you suffer. It does have a purpose.